Today, we're going to talk about wave intensity. So, how do we calculate the wave intensity? So, wave intensity is just equals to power divided by the surface area. So, this I is going to be the intensity. We just read it. Okay, so this I is going to be the intensity. This P on the numerator is going to be the power. And this SA is the surface area here. And this power is going to be power. Okay, so what is power? So power is basically what's in unit. And it is energy per time. Or we can say power is equal to work over time. It is how much work you do for time. And that will be equivalent to power. So let me highlight this. I'm going to emphasize the power. So this is work and this is time. So time is measured in seconds. And watts is its unit is going to be, work is its unit is going to be energy, joules. So now let's talk about inverse square law. So inverse square law states that intensity is inversely proportional into the distance. So if the distance increases, the intensity is going to decrease. If the distance decrease and the intensity is going to increase. So imagine if we have a source here. Let's put some tree source. So the source of this is going to be 1 meter. So it will have an intensity of 900 watts per square meters. And when it increased by 1 meter, it's going to be 2 meters. The intensity is going to be lower. It's going to be 225 watts per meter squared. And if the distance is going to be far of more, and it's going to be 100 watts per meter squared. So as we can see here, they are inversely proportional, inversely related to each other. So let me just write some notes here. I is going to be the intensity, R is going to be the distance, A is going to be the amplitude. So that's basically it. A lamp emits 100 joules of energy in 4 seconds. What is the rate of energy emitted by the lamp? So this is going to be power is equals to work per time. So the work that have done by the lamp is going to be 100 joules divided by the 4 seconds. So this is going to be 25 watts, or we can write it as joules per second, 25 joules per second. What is the intensity of light source 1 meter from the lamp? So we're just going to use the wave intensity equation. So let's say we have a light bulb here, and it is basically a sphere. So the surface area is going to be 4 pi r squared. So the intensity is going to be power, which is 25 watts, divided by the surface area of the sphere, and the radius squared is going to be 1. So it's going to be 1.9889 watts per square meter squared. Okay, so this is the intensity of the light source. What is the intensity 2 and 3 meters away from the lamp? So this is just the demonstration, visualization of the equation that we have earlier. I just plug in 2. So we have here is going to be 0.49. Okay, let's add some numbers. Watts per square meter squared. So as we can see here, as the distance increase, the intensity just get lower. So the intensity on 3 meters away from the lamp is going to be much lower because its distance is going to be greater. Okay, now we got this 0.221 watts per square meter. So that's it. So you can see here. The intensity of the sun at a certain location on Earth is 2400 watts per square meters. How much solar power can be received by a rectangular plot of land that is 60 meters by 80 meters? So let's say we have a rectangular plot here, and it is 60 by 80 meters, and our sun is just producing some light rays into that rectangular plot. So we're going to calculate the solar power, which is going to be the power, of course. So we have a given of intensity, and we are going to calculate its surface area too. So intensity is going to be 2400 watts per square meter squared, and the power is just there. So the surface area here is going to be 60 multiplied by 80. So this is going to be around million. It's 11,526,000 watts per square meter squared. I mean, no. Okay, let's just watch. So this is the power that is being received by the rectangular plot. So it is a lot because it is the sun. How much energy in joules can be collected in a year? So how much energy will be collected by this rectangular plot in a year? So what we can do here is just conversion process. We're just going to use the unit of under instead of watts, and we're going to convert this into a year. So we have 60 minutes, there's 1 hour and 60 minutes. There's 24 hours in one day. And in one day there is approximately 30 days. Okay, so we have 1 month. I mean, in 1 month there's approximately 30 days, and we're not going to write the leap year. So 12 months over 1 year. So there you have it. We can just cancel some units here. Seconds will cancel, the minute will cancel, hour will cancel, day will cancel, month will cancel. So what we left here is joules per year. So now, typing those things in our calculator, we have this final answer. So this is pretty much a lot, of course, because it's been a year, right? How about a decade or whatsoever? So this is 3.584834 times 10 raised to the 14 joules per year. So that is how much energy. Too bad my laptop has freeze, so we have a problem here. You can just pause it up and then continue this. What am I doing here? Continue this. So this is the answer for this problem. You can try it though. Oh, now let's move on into another one. I can bring it back though because I didn't record the screen. Too bad. Okay, now let's calculate this. The amplitude of a wave is 60 at a distance of 4 cm from the source. What is the amplitude at a distance of 1 cm, 8 cm, and 6 cm? So I did change the inverse gorilla on the top. I did write the equation wrong, but it's now fine. Okay, now let's calculate the distance. Oh no, not the distance, but the amplitude at 1 cm. Okay, so what we can do here is just use the inverse square law equation. So we got this. Then, so to make things easier, let's just solve for the amplitude number 2, a sub 2 squared. Okay, so we just cross multiplied it. Now we can just divide both sides and take the square root, and then that's it, we have the equation. So a sub 2 squared is going to be r sub 1 squared, then multiply by a sub 1 squared, all divided by r sub 2 squared. Now if we're going to take the square root, all of the raised to the second power will cancel. So we got this. Now we can just plug in everything that we know. So on the first problem, we're going to find the amplitude if it is at the distance of 1 centimeter. R sub 2 squared is going to be 1, so this is going to be 240, right? So it's going to be 240. So it's basically in its inverse square law. If the distance is close, the amplitude will be much more bigger or greater. So if the amplitude just got bigger, it's just basically on the close distance. Why do I keep saying radius? It looks like a radius because it is an R. Okay, now let's calculate the amplitude when the distance is around 8 centimeters. So okay, so now the distance is going to be still 4 on the R sub 1. Okay, sub here. And we're going to change the R sub 2. So if it is around 8 centimeter, the amplitude is going to be in decrease. It will decrease because it is far from the source. Now lastly, let's calculate the what if it is 6 centimeter. So what we have here is going to be 40. Wait, I did forget. There you have it. And that's it for this video.